form. All right. All right. Now I just recalled here symmetric and Hermitian. Form on the V, we call it symmetric if phi xy is phi yx for all x and y. And this case occur when your field K is arbitrary and the kappa is identity. And Hermitian case occurs when your field is K and there is the involution which is not identity. That is what I try to make. So many cases are coming together here if you read the first page of the assignment sheet. And that simply means this. And those who don't want, those who are not interested in other fields other than real and complex numbers, fine, they can take real and complex numbers and do it. And but the important applications also include finite fields, and nowadays they are very important in arithmetic geometry and etc. So on. So those who are interested, they can pursue the general cases, otherwise stick to R or C. And symmetric means the Gram's matrix with respect to basis is symmetric, and otherwise Gram's matrix in case of Hermitian, it is Hermitian means the matrix equal to conjugate transpose. That's written here. So either one can look at matrices with this property and then see this is one-to-one correspondence between the forms and the matrices. The Gram's matrix will determine the form. You can define the form by defining it on the basis elements. So that is the idea. And it is better if you do it coordinate free, means don't choose a basis beforehand. Choose it when you need it. All right. And see, all these I was preparing. So first of all, this symmetric Hermitian, the motivation came because perpendicularity is not a symmetric relation. And if you want it to be symmetric relation, then this will come out of that. That is what all the time I tried to say that. But I don't know how much I succeed that you will. Sorry. Anybody has a question? What I tried to say in the last lecture, the point was how did Hermite came to these forms? And the difficulty was because that perpendicularity relation is not a symmetric relation in general for arbitrary form or arbitrary statistical linear function. And he came up with this condition and then it became these definitions. Symmetric in case of real case and Hermitian in case of a complex case. When the involution is a complex conjugation. But of course, one can also study symmetric bilinear forms on C also. In that case, the involution is the identity map of C. That is what I tried to say. And actually, I wanted to finish with this theorem. This is, you might have seen this theorem, so I am not going to prove this because otherwise we will never reach the goal. And remember, the goal is we want to relate the zeros of the polynomials with the forms. So that is a connection between linear algebra and zeros of the polynomials. And you will see it, I am preparing today. All right, so what is the decomposition theorem? Given a Hermitian form on a finite dimensional K vector space V, then there exists an orthogonal basis of V. And when you say orthogonal, that means it is with respect to the form phi. And this precisely means this V, the vector space V, we have decomposed into orthogonal sums of these one-dimensional subspace. This is for a real and standard real vector, finite dimensional real vector spaces. You would have seen this, and that is a standard process. The process was Smith orthogonalization. That was it. and it was similar to this. So I am not going to prove this theorem. All right. Now, what am I going to do today? So this was. If anybody has still any question, I will be happy to answer. Anybody has a question?
Shashank Shukla, you are unmuted. So if you don't have any question, you can mute.
Honestly, I am not able to hear you.
Sir, actually there is a guy, Shashank Shukla, who is unmuted, but he's not speaking anything.
Shashank Shukla.
He should mute himself. I am saying that.
Oh, he should mute. Shashank, can you mute yourself? All right. I don't know whether he hears or not. I don't know, but we'll continue. All right. Now, what is the plan today? Okay, the plan today is the following. And again, I am assuming that you know the terms like positive definite, negative, also semi-definite, positive definite, semi-definite. Similarly, this and indefinite. And if your field is R, it's fine. Or more generally, you should have a real closed field. Because real closed fields, if you note the footnotes of the assignment, it has an order. And with respect to that order, we can say this. For example, positive definite should mean that phi of xx is positive for all x in V. Similarly, semi-definite means bigger equal to 0. Of course, this x is not 0. And similarly, the other indefinite means you can have one x for which phi xx is positive and the other y so that phi yy is negative. So these are the standard terms. And I've seen some of your exercises in the other lectures that all these you are well acquainted. So I am not going to spend on time on this. All right. So what am I going to use? What am I going to do today? I will first tell you the plan and then we will execute. All right. So we are starting with the form phi. And I will say Hermitian. Hermitian on finite dimensional K vector space. Where this K is either R or C, you take it. In this case, there are two cases in this. All these three cases are included when I say Hermitian. So in case of R, it has to be symmetric. In case of C, when the kappa is identity, that is also symmetric. And in case when kappa is the conjugation, then it will be Hermitian. Then we should insist that it is complex Hermitian. This is what I tried to say in those. And I actually wanted to add the other fields also, which are interesting. For example, real close. So, all right. Now, what do I want to do? To this phi, I want to attach a pair of integers, p comma q, where p and q are actually natural numbers. And of course, this is on, and n is the dimension of. And also the r, other integer is r. And r is rank of phi, which is by definition, it is rank, if you want, it's the rank of the Grams matrix. With some fixed basis. Well, and this pair we will call type of phi. Type of phi. And of course, we have this rank. And how do I define them? Because I want to choose a good basis. That's always the case in linear algebra also. When you have a linear map, you want to find a nice basis. Why do you say nice? Because your calculation becomes pleasant and easier. You don't remain with the same matrix, because even if somebody gives you a matrix and you want to study that matrix, you look at the linear map defined by that and find other basis of that linear map, so that the matrix of F with respect to that new basis will be nicer. And then original matrix and this new matrix, they are conjugates of each other, and therefore the invariance will not change. So you might calculate with this new matrix, and the advantage will be the calculation will be simpler and also faster, even if you want to do it on the computer. Given arbitrary matrix, if you want to feed it to the computer and compute the determinant, it will not be very convenient. Your computer may not work also. All right, so the same philosophy here also. I want to find a nice orthogonal basis so that the Grams matrix looks nice. And from that Grams matrix, you can immediately read of this P and Q. So that is very important thing. That is due to Sylvester. So that is called Sylvester's law of inertia. All right. So what is it? So this you see, if you want to see originally track the reference, it will be 1878. So it was long ago. All right. So what does it say? So I will use the same notation. Given a phi Hermitian matrix and a finite dimension k vectors on this, so there exists a basis let me call it X, means x1 to xn of V, such that is of course orthogonal. And whenever I use the word orthogonal, that is with respect to the given form. So that means phi of xi, xj is 0 for all I not equal to j. I am not saying orthonormal. Orthonormal, you will have difficulties. In case of complex numbers, fine. For orthonormality, you will need more assumptions on the field. You will need algebraically closeness in general. All right. you can find an orthogonal basis of V, orthogonal with respect to phi, such that the Grams matrix GR phi X, this is what by definition it is phi XH. This is the Grams matrix. This has a nice form. This looks like E P Q N. Now, what is this notation? So this the down suffix shows it is the n cross n matrix, and this PQ says that you will see. This is the diagonal matrix. So I will write dag. Dag is for diagonal. 1 1 1. Three times. Then comes -1 Q times, and then comes 0 0. That is, so that the Grams matrix is nice looking. I wrote it in this form because to save the space. So otherwise I would have written like this. Then -1, and then zeros. And then remaining things are zeros. So this is block is there are three blocks. This is P by P, this is Q by Q, and this is, of course, I know the total this, so therefore can see that P plus Q equal to the rank, and the number of zeros will be equal to n minus r. So this size is n minus r. So, and in fact, we can also describe P and Q nicely. Okay, before I give a proof, also I will tell you this P is called, so I'll write on the next page. So this P is called inertia index. See, some of these words are coming from physics. Unfortunately, I don't have enough time to give some examples from physics that would have been helpful. But because of I want to finish the main thing, therefore I won't have much time. All right, Q is called Morse index. The of phi, and P minus Q is called the signature of phi. And P comma Q is called the type. This is called a type of phi. And I want to relate the signature with the number of zeros. That is why all these things. And in the exercise set 2, which you will do today, there will be a lot of problems. There are a lot of problems. In fact, I was I was confused which one to choose. There were so many of them are interesting. So I listed many of them. But depending on your choice, depending on your interest, depending on your energy, depending on the time you want to spend, choose some of them and do them. And many of them I try to write the solutions. They are hints, but most of the hints are almost solutions. So, and I would also appreciate if you find a misprint and report it to me. That will be a good award for me to improve myself. All right. So we will prove this. So actually, I will write down what how to find this P and Q. In fact, P is the maximum of so let me write in the notation so that will save some time for me to write. P is equal to max of dimension of V prime. So V prime is a subspace of V with phi restricted to V prime is positive definite. Subspace. And Q, once I wrote this, it will be easier what to guess Q. Q is maximum dimension V prime subspace of V with phi restricted to V prime is negative definite. And that's it. If you do this, then R is, R, and therefore N minus R is determined and so on. In particular, P and Q do not depend on special choice of the orthogonal basis. X, which is x1 to x. You see, try to get the point. Why did I say P equal to this and Q equal to this and then in particular? Because normally what happens? See, if you try to prove this, there exists a basis, says that the matrix is this. Suppose you prove this and don't say this P and Q is what? Then people will ask you, if somebody finds another orthogonal basis, then you get another P and Q. Now why should they be same? So you'll have to prove they are same. Then only they are well defined. But if I prove directly that P is this and Q is this, then it doesn't depend. The definition of P and definition of Q doesn't depend on the orthogonal basis. So no matter what orthogonal basis somebody chooses and come to that P and Q, they are unique. And therefore they are the invariants of the form. All right. So I only have to prove that P is this and Q is this. Because then problem will reduce to positive definite. And then you know it already. That clear? All right. So proof. Unless you speak out your difficulties, I cannot make out whether you have understood, not understood, you have comment, and so on. Proof is very, very easy. All right. So let us call P prime. P prime this side. I want to call, will write. I want to call this side is P prime. And this side is Q prime. Then I want to prove P equal to P prime, Q equal to P prime. What is P? P is this. The number of P's on the one, number of ones on the, that is the P. Number of minus ones are the Q. So you see here, you see it here. On the, this if the matrix is this, you know already all, if I take this subspace generated by these vectors corresponding to this first P entries. So that is what, that is x1, x2, xp. So if you take subspace V prime equal to kx1 plus kxp. This is the notation for subspace generated by x1 to xp. This is a subspace of V, and obviously phi restricted to V prime is positive definite. And P prime is the maximum. Therefore, it is obvious that P is less equal to P by definition of P prime. But I want to prove the equality. So let us take, I have to prove the other inequality. So let us take, let W be a subspace of V such that phi restricted to W is positive definite. Then I should prove that the dimension of W, what we want to prove. Dimension of W is less equal to P. Isn't it? I want to prove that. And once I prove that, I get the other inequality. Because then the maximum, all these guys are bounded by P, therefore the maximum will be bounded by P, therefore P prime will be bounded by P. And therefore we get the another inequality. All right. So we want to prove that. Now look at the complement of V, complement of W in V. So look at U prime, which is generated by kxp plus 1, etc. kxn. This is the complement of P in complement of W in V. And also, because it's a complement, it is obvious that W intersection U prime is empty. Not empty, 0. Therefore, one, this is this, then I know what is the dimension. Dimension W. Dimension W will be less equal to n minus dimension of U, which is P. So done. And similarly, we prove the other inequality. Similarly, this one. This Q is equal to Q prime. Q equal to Q prime.
Sir, is that U or U prime?
Which one?
Dimension of
sorry.
W is less than.
Yeah, that is U prime. I don't know why I called it prime. Actually, not necessary to call prime. No, there is no U. So I call it prime.
Sir, how is that equal to P? Can you explain that?
Which one?
N minus dimension of U.
What is dimension of U? You know. It is n minus p.
N minus
You
P.
can
Yeah, yes.
don't think in a complicated way. Things are very easy. So you start with the arbitrary orthogonal basis that we know from the last lecture. That is what I said. I wanted to prove this, and then do that. So it's very easy. Okay, let me write one corollary. Corollary you can write in terms of, okay. So let us write one. Let me write one corollary. So again, phi, the same notation, Hermitian form on a finite dimensional vector K vector space. K means R or C, you know the notation. And suppose X is a basis. X equal to Xn, basis of V. That's given. And then you have this Grams matrix, GR phi X. This is Grams matrix. This is with respect to this basis. Then phi is of type PQ. If and only if GR phi X is congruent to this matrix E PQN. What does congruent means? I think you know it. When do you say two matrices are congruent? So if I have two matrices, so I will write down this. This means so that is G, this matrix GR phi X and this matrix. How are they related? That is A transpose times A bar. And actually tell you what is this matrix A also. This matrix A is actually, so congruent, that means there exists a matrix A which is in GL and K such that this. And what is this matrix you can take? A is a transition matrix. See, you may have to change this basis to make it into this form. That is what this means. And that means This A will be nothing but the transition matrix. Transition matrix from the basis X to whichever new basis you will choose, which will have this property. Which will have this property. This property. This, that the matrix will look like this. All right, so that is what in particular. So there you can, all these you can state in terms of matrices, but I am not going to do that. Is that clear, or still some explanation one wants? Please ask. Otherwise, I will go to the next, because yeah, I have to finish. I have to at least come to a reasonable. All right. So the next one. So what is a non-degenerate case? So let us little bit digress little bit. So in a non-degenerate case, that means phi is non-degenerate. That means the rank is, so rank is n. N is the rank. But that we know rank is p plus q. So this R is 0. That is a bad notation. This R is not the rank. The R is the, what did I write there? No, I wrote it correctly. N minus R is 0. It's correct. So that means fine. These are the rank. So this is the non-degenerate case. Then from this you can read the determinant. The determinant from the this one. If it is type PQ, so this non-degenerate PQ is the type. Then the determinant of Gram's matrix, arbitrary orthogonal basis. This I want to write down. And this this is from here. I want to relate from here. So this is equal to -1 power q times mod of the determinant of a square, because you see a bar and a, their determinants, you know, a bar, this will be determinant a, this will be determinant a bar, but that bar will come out because bar is a automorphism of the field, so it respects multiplication and addition. Therefore, I will take the bar outside the determinant. So determinant a times determinant a bar, but that is the mod of the determinant. That is what mod of the determinant square. And therefore, if I want to know the signature of this determinant, so signature of, see, this is a real number. This is a real number. So sign means positive or negative. Signature of the determinant of GR phi x, this will be equal to -1 power q. So therefore, if you already know the sign of a determinant, signature of the determinant, when I say signature means positive, negative, then that will determine the parity of Q. So therefore, the sign of GR, not GR, determinant GR, determinant GR phi X determines the parity of Q. Parity means, I hope everybody know parity. Should I assume that you know or should I define?
Please define, sir.
Parity means evenness and oddness. That means mod 2. That is the parity.
Thank you, sir.
That means when you read Q mod 2, that's uniquely determined. No? That is what it means. All right. And this actually this observation gives a nice criterion to determine the signature of the form. This observation, knowing the signature of the determinant. All right, and that is precisely the Hurwitz criteria. So Hurwitz criteria. Those of you who have studied theory of equations in a classical day, this is not so difficult to grasp them for that. Hurwitz. All right, what is it? So phi Hermitian form, Hermitian form on V is a K vector space. Dimension is N. And suppose X is a basis. Basis of V. And we have this ground matrix. This is this matrix. This is in N cross N matrix. And suppose, now I want to put some assumption. So suppose that the principal minors of this Grams matrix. What are the principal minors? Let me write them DIs, capital DI. That is by definition determinant of you start with phi x1 x1, phi x1 xi, xi. I'm writing ith minor. And then take phi x2 x2, x2 x1. You go on to phi x2 x2. This is 1. This is xi. This is 1. This is the first row. Go up to ith column. And so on. Take the ith row. ith column. This is the principal one. Determinant of that. So if your matrix is like this, these are the principles. So 1 by 1, then 2 by 2, then 3 by 3, and so on. These are the principal ones. This is 1 cross 1, this is 2 cross 2, this is 3 cross 3, and so on. So I is running from 1 to n. And these DIs are by definition, they are elements in the field. And suppose we are assuming all are nonce. DIs are non-zero for all I from 1 to n. That is the assumption. That is what we are supposing. In particular, we are assuming the Grams matrix is as a non-zero determinant. Dn is the determinant of the Grams matrix. It is non-zero. So it is a non-degenerate case. So remember here, in particular, by our assumption, phi is non-degenerate. By assumption. All right. So we have this sequence. So I actually starts with 0. Why not 0? Zero means empty matrix and determinant 1. So you should remember here. Somewhere you should remember. Remember that empty matrix. I should not write that like phi, but empty matrix. Let us write in words. Empty matrix determinant as determinant equal to 1. So what do we have? We have a sequence. So D0, which is 1. This is D1, D2, and so on. DL. So the last one is the determinant of the Grams matrix. Then our interest is to compute the type, because I want to relate type with the number of zeros of polynomials. That is my next lecture. All right. So then phi is of type n minus q, comma q, where q is the number of sign changes in the sequence this. Let us call this sequence a star. Don't worry about the proofs. First, try to understand the statement. I hope everybody knows what is the sign changes in a sequence. This is a sequence of whom? This is a sequence of real numbers. Why? Why can somebody say why all these DIs are real numbers? They are determinants. And the symmetric. These matrices are symmetric, no? Or Hermitian. And then we saw determinants are real numbers. Therefore, they are real numbers. Therefore, sign, signature, sign positive or negative makes sense. And sign changes means you start with this one. Look at D1. If D1 has a positive sign, there is no change. If D1 has a negative sign, count once. If D1 is 0, you throw it out. That is how you count the sign changes in an arbitrary real sequence of real numbers. First of all, look at that sequence, remove zeros from there. But in our case, we don't have to remove anybody because all these DIs are non-zero by our assumption. And therefore, you just have to start. D0 is positive. If D1 is positive, go to the next. Till you get negative, then you count one and keep doing it. So you just have to count how many times sign I change. And that change of sign is the Q. And then the assertion says that the type of phi is n minus Q comma Q. Once you compute Q and you know the form is degenerate, non-degenerate, then you know what is P also. P has to be n minus Q. That's it. So we have to prove very less with all these remarks. And we'll see 2-3 lines are enough. Anybody has difficulty, I will still explain if it is fast or proof. Anybody want to ask question before I start the proof? This is very, very important theorem. And this I will use it. And this is also classically related to, if you remember your BSc days, if you have learned theory of equations, the so-called Descartes rule of sign. But anyway, I am not using. In fact, I will deduce it. Any question?
No, sir.
Anjana, tell me. Ask. Don't hesitate. Oh, no question. Shall I go on?
Yes, sir.
All right. All right. So Dn is non-zero. So since phi is non-degenerate. Dn is non-zero, so phi is non-degenerate, and let PQ be the type. P the type of phi. And therefore P plus Q has to be n. So therefore this guy is n minus Q. But now I want to prove Q is the number of sign changes in this sequence. So with this, we need to prove that Q equal to number of sign changes in the sequence D0, D1, etc., DL. This is one. And all these guys are non-zero, that we know. So I want to compute the sign changes. How many times sign changes? And that has to be the Q, where Q is the Morse index. That is what we need to do. Right? Watch out, I am not cheating you. If you feel I am cheating, ask. All right, how am I going to prove this statement? Yes, John, you want to ask? All right. How am I going to prove this statement? I am going to prove this statement by induction on n. Proof by induction on n. So induction should start somewhere. And where does it start? Start n equal to 0. I would like to start induction n equal to 0. It's trivial for n equal to 0. But some of you, if you have difficulty, why? You can enter trivial for n equal to 1 also. Because n equal to 1, there is d1 and d0. So, if d1 is negative, d1 is negative means what? That means that, so d1 is this here, determinant, but that is that entry. If it is negative, that means that p has to be 0. So this has to be negative number. Sign changes. So it's clear. For n equal to 1, also it's clear. So clear for this. And now I have to prove the inductive step. Inductive step from n minus 1 to n. That means I am assuming the assertion for n minus 1 and proving it for n. And therefore, I am going to restrict my form phi to v prime. V prime is what? Forget the last vector. So that is subspace generated by x1 to xn minus 1. So restriction. So phi restricted to phi prime equal to phi restricted to this subspace. Now v prime is of dimension n minus 1 and the principal minus doesn't change. You see, principal minus will not change.
Sir.
Yes.
Sir, actually, I have few queries.
Please ask.
Sir, in the previous theorem.
Which previous theorem? Sylvester.
Yeah.
Tell me.
Here we have taken a subspace W.
Yes.
Yeah. In the proof, we have taken the subspace W.
Yes.
We don't know the dimension about W, but we have taken U, which is complement of W, and we have taken U to be the subspace generated out of xp plus 1 to xn.
Very good question, but think a minute.
So it directly says the dimension of W has to be equal to P.
No, wait. I said W intersection U is 0, that you agree or not?
Yeah, that is fine, because they are complement subspace.
I agree, I use this word. Complement is not a correct word, so forget that. Now look at this. I start with W. Phi restricted to W is positive definite, and W, we want to prove dimension of W is less equal to P, isn't it?
Yes, sir.
Now look at U. U is this. Generated by xp plus 1 onward xn.
Yes.
Now, do you agree W intersection U is empty, 0.
That we don't know because here we have not assumed that U is
No.
complementary subspace.
What? How is the basis? You see here. Look at this.
It's from x1 to xn.
Xp plus 1 to xn.
That is for U.
Yeah, that's for U. But then U that cannot be, that cannot intersect with W, because if it does, then positive definiteness of phi restricted to W will tell that for some W which is also in U, phi UU is positive. On the other hand, this tells you that cannot be, because U is here. There minus 1, minus 1, minus 1, and 0, 0, 0.
Okay,
if
okay.
at
You
all
have
you-
taken U. Okay. Yes, sir.
Isn't it?
So you have taken U caused by those Q elements.
These ones precisely, isn't it? P plus 1
Okay.
onwards, no? See here, that is what I wrote. Here. Here.
Okay, okay, sir. Okay, since we assume that to be P, here from P plus 1 you started. Okay, okay.
Exactly.
I thought what if it intersects?
But
Like there exists a,
good that you asked me, because I had used that wrong word here, complement. That was not a compliment.
yeah, I took it as compliment.
No,
when
no,
you
no. I
said.
also wrote that is not your fault alone. I also
Yes, sir.
wrote, no. So,
So only it was clear that W intersection U has to be singleton 0.
yes. And you see,
Okay.
it is clear because we only want to prove the inequality only. So we don't have to take the. Okay, fine. It's clear now.
And one more, yes, sir. One more question.
Yes, please.
Here, do we assume anything on phi that phi is positive definite? No.
No, we don't.
But on the restriction of V dash, how do you say that it is positive definite?
Look at that. See, we have chosen a basis. No, we have already chosen a basis with this property. No.
Such that EPQN is the Gram matrix.
Yes, we have already chosen
Yes.
that. Oh,
Okay,
and how did we?
okay.
Now you should also ask the question, how did I choose that? Because of the decomposition theorem.
Yeah, that is true. That's
And then
true.
whichever entries were positive, I made them one by usual standard process of orthogonalization.
Gram-Smith. Yeah, Gram-Smith process. Yes.
So.
Okay, now it's clear. Yeah, thank you, sir.
Very good. Now can I go on?
Yes, sir.
Okay. Now, as a result, I don't know whether you paid attention to this. You paid, or shall I repeat or go on?
Sir, it would be good if you
All
repeat
right.
once.
All right. Now what? See, we want to see now. These all okay, fine, but we want to compute. When computation of the type, we need some handy criterions. How do we compute type, for example? That is the main problem, no? So if you start, so this Hurwitz criterion will be handy to compute the type of a Hermitian form. So start with the Hermitian form on the vector space, n-dimensional. If we choose a basis, take any basis and look at the Grams matrix. Don't choose a basis. Take a look at the Grams matrix, whatever it is. And now I want to assume that all principal minors of this Grams matrix are non-zero. So principal minors means you see this picture. They are the principal minors. That means all these determinants are non-zero. First of all, note that these principal minors are real numbers. That is because you see the minors are symmetric. And then you would have seen symmetric matrix determinant and so on. No? All right. In particular, Dn is non-zero, therefore phi is non-degenerate. The rank is p plus q. And we have the sequence of real numbers: 0, d0, d1, d2, dn. This is the sequence of real numbers we have. Just by looking at the sequence, I want to write down the type of that form. That is the idea. Then what is the assertion? Then phi is the type of n minus q, comma q, where q is the number of sign changes in the sequence, this sequence. And what is the sign changes means? Sign changes means that means you start here, look at the sign of D1. If D1 is negative, you count it 1. If D1 is positive, don't do anything. Go to D2 and keep doing it. How many times it has crossed the axis? That is how you are told, no? That is the sign change. In general, if you have a sequence of real numbers, finite sequence, and if you want to compute the number of changes in the sign, you remove the zeros from that sequence. For example, if your sequence is that zeros are not there in our, but in general, so suppose your sequence is like this: 1, 0, -1, 2, -3, -2. Suppose this is your sequence. Now you can put zeros also in this one. 2, they're all comma 0, 0. This is your sequence. Now let us compute the number of sign changes. So first of all, remove the zeros. Forget these guys. From here to here, 1. From here to here, another 1. From here to here, another 1. From here to here, no. So how many times? So 1 here, 1 here, and 1 here. So 3. Understood? That is how you compute the number of changes in the sign. So we have this sequence of real numbers, and that Q is, I have called that Q is the number of sign changes in the sequence. And then our claim is n minus Q, comma Q is the type of file. That is the claim. That is what I want to do. That is Hurwitz's criteria. All right. So what is the proof? So note that Dn is non-zero. So first of all, we have already noted this. C is non-degenerate. And suppose P comma Q is the type of phi. Non-degenerate, therefore P plus Q is N. And therefore, what has to be proved? We need to prove that this Q is the number of sign changes in that sequence. That is what we need to prove. Isn't it? Who was the girl who was talking? Shanmukha Priya, right?
Yes, sir. Now it's clear, sir.
All right. This assertion, I am going to prove it by induction only. And I said n equal to 0, it is trivial. N equal to 1 also, it is trivial. So, therefore, to complete the induction, I have to prove the inductive step from n minus 1 to n. Okay, that means I am assuming for n minus 1. So you restrict the given form to the subspace generated by x1 to xn minus 1 for that form. And then this sequence will not change. Only the last entry will change. Isn't it? Because you look at the principal minors. They will not change. The determinants of the determinants of this guy. So only the last dn will change. Agreed? All right. So what needs to be proved then? So therefore, by induction hypothesis, type of phi prime will be equal to n minus 1 minus q prime, comma q prime, where q prime equal to the number of sign changes in the sequence D0, D1, Dn minus 1. This is 1. Agreed? This is by induction hypothesis. Because this is a form on this vector space V prime. Right? Now what do I want to apply now? Sylvester's law. So what do the Sylvester's law say? This for this form, this integral is that P, where it is 1, 1, 1, 1 so many times. And here this one minus 1 so many times. So that is what the Sylvester's law says. So therefore I would say Sylvester's law will tell. So by Sylvester's law, n minus 1 minus q prime will be less equal to n minus q. Do you agree? See, this form is on this vector space. So if this is the type, what will be that EP this is your P prime. So it will be 1, 1, 1, 1, 1 so many times, and then minus 1 so many times, and all are exhausted because the form is non-degenerate. And now when you go to phi, you have to add somebody here. Isn't it? You have to add somebody here. And what was n minus q? N minus q, our notation is n minus q is p. So already 1, 1, 1, 1 are so many times. So this can be positive or negative. If it is positive, then this will be strict inequality. If it is negative, it will be equality. So this is clear. Is that clear? I get one couple of seconds pause. Not only this, and q prime will be less equal to q. So you see here, this guy can be positive, then it is added to this positive one, that is this inequality. If this guy is negative, it is added to this one. So if this is positive, this will be strictly less and this will be equality. If this is negative, this will be strictly less and this will be equality. That clear? Very simple. And what does this both this inequality? Therefore, that implies q prime is less equal to q. And from here, if you shift to the other side, this is less, cancel n, shift this. This is q prime plus 1. Right? And what is the sign of the determinant d, sign of the number dn minus 1? Let us see what is the last one. But that I told you, this observation here. This observation here. In the non-degenerate case, sign of the Gram's determinant is minus 1 power of the Morse index. So that I am applying to the C prime. Applying it to phi prime. So sign of the Grams matrix, the determinant of the Grams matrix equal to -1 power most index of that Q prime, which is most index of the phi prime, which is Q prime. This is by the observation after Sylvester's law. This observation. Listen. Therefore, the sign of the determinant of the Grams matrix determines the parity. All right. So that we got. And then we are interested in finding out sign of Dn. By the same observation, sign of Dn is -1 power most index of phi. That is Q. That was our notation. Here. These were the type. Therefore, this P is the inertia index, this Q is the most index. Therefore, by that non-degenerate, therefore sign is this, therefore sign is this, and sign is that. So Q and Q is in between. So if Q is equality here, so I say then the proof is finished. What in between?
Sir, how about the degenerate case?
1 minute. Let me understand your question. Please ask one by one. Which step you want?
No, here we have started with non-degenerate case, right? Phi being non-degenerate.
Not started. By assumption is in particular it is non-degenerate. Our assumption is much stronger than the non-degenerate. You see, our assumption is all these principal minors are non-zero.
Yeah, okay.
In particular, the
Yes,
determinant is non-zero. That is the meaning
Yes,
of
sir.
phi is non-degenerate. All right?
Yes, sir.
And now, anything else? And also Sylvester's law is also used. The Sylvester's law we have applied to, if you want, you should remember, you should write here, applied to phi prime, which is phi restricted to V prime. I call it V prime now. Yes. So you see, we have this information, and from here, you know, if Q equal to Q prime, then they have the same sign, so no need to count extra. If it is this, then you have to count extra, which is, that is what we want. So this whose Hurwitz criteria. All right. Since nobody asked me, I will go on. All right. Now I want to prove one interesting. So you should, I don't know what to call it. This is about matrices. I have to bring in the polynomials. So let us take K to be a field. And I will denote KT to be the polynomial ring in one variable T. Polynomial ring in one variable T. And I take the polynomials. Fij, capital Fij's are polynomials in one variable. 1 less equal to I, j less equal to n. And I want to form the matrix Fij. This is the matrix. This is the matrix. Remember, this is not over a field. To start with, this is Mn Kt. So polynomial entries. And I want the symmetric. So I assume that Fij equal to Fji for all ij. All right, and fix small s in K. And look at the matrix. I want to specialize this matrix by putting capital T equal to small s. So look at this matrix. Fij evaluated at small s. Now this will be n cross n matrix over K. And not only arbitrary matrix, it will be symmetric. And assume it is non-linear. Assume that determinant of Fij evaluated at x is non-zero. That is the form. See, a matrix symmetric, therefore it will define a form on n-dimensional vector space over K, and we are assuming this form is, this is the form on K power n cross K power n, if you like, to K, and this is non-degenerate, symmetric. Therefore, we have the type of phi. And the type of phi will look like n minus q times q, because it is non-degenerate. Or you also can say it is p comma n minus p. Whichever coordinate you fix, one coordinate, the other coordinate will be determined by that coordinate and n. So I will assume it is, I will use this notation. All right, so this is the type. Now, what do we want to prove? Then, see, we have so many assumptions, but the assumptions are very clear now. So then, there exists epsilon positive. Let me also tell you, it doesn't matter which you take K to be real numbers, complex numbers, or more generally real closed field, all of them have topology. Real numbers, complex numbers, of course, you know the usual topology. A real closed field also will have topology because it has an order, and that order topology. But if you don't want to think about it, don't think about it. You consider only real and complex case. All right, then there exists epsilon positive such that look at these symmetric matrices. Fij evaluated at T and T is varying in the interval. Which interval? This one. Open interval S minus epsilon, comma S plus epsilon. S was that where I fixed. Where I fixed this matrix, it is symmetric. We are assuming it is non-degenerate. We have the type. Then there exists epsilon such that all these symmetric matrices in this interval have the same type. That is the assertion. So, such that there exists epsilon positive such that the type of all these matrices in this is the same, is equal to type of phi which we have denoted n minus q comma q. That is the assertion. So what does this mean if I have to say it in one sentence? That means being a type PQ is an open property for non-degenerate symmetric forms. So I will write it here. So this means being of type PQ is an open property for non-degenerate symmetric bilinear forms on K power n. Don't worry about the proof. Just worry about the statements, whether you understand and the meaning of that statement.
Sir,
Yes.
here the field K is the real number field R.
Take real numbers.
Okay.
Take R or take C. Doesn't matter.
Sir,
Yes.
if we take the complex numbers instead
Sorry?
of this, if we take this K as complex numbers,
Yes.
then in case of real numbers, we had this interval S minus epsilon and S plus epsilon. In case of complex numbers, can we expect a disk?
Don't take complex numbers. See, I don't want to understand you about topology. So forget complex numbers also. Doesn't
Okay,
matter.
sir.
Or if you want, you can write C as R cross R.
Okay, sir.
Doesn't matter. Even if you understand for real numbers, fine. See, the other general cases are just easy extensions. Like, see, whether you take complex numbers and the usual topology or R cross R and the usual topology are the same.
Yes, sir.
All right. All right. So the time is up, but think about the statement. It is, and only tool we have is Hurwitz criteria. So proof. But time is already up, so I don't want to exceed so much, because yesterday when I exceeded probably 1 or 2 minutes, this meeting was closed. So I don't want to be in the same situation again. All right. So Hurwitz criterion is the hint if you want. Those who are interested, we will see in the beginning of the next lecture, or we will discuss in the today's tutorial session, whichever is convenient. All right, with this, I want to stop. It's already time. And if you have any question or anything that you should ask in the tutorial session. Fine. Thank you.
Thank you, sir.
Okay, bye. Don't hesitate to ask questions.